Today, I would like to explain about the concept of activated complex. So, this is the part of the chemical kinetics. We know there are different theories are existing to explain the concept of the chemical kinetics. That is Arrhenius theory, then collision theory, then Lindenmann theory. So, I would like to concentrate on this topic, that is concept of activated complex. So this theory was developed by Polanyi Irene, and they developed a theory of reaction rates based on fundamental properties such as dimension and masses of reactant molecules. So the fundamental idea of the theory is that the reagent molecules must first form an activated complex. In Arrhenius theory, we know that the reactant molecules will goes into the transition state. But according to this activated complex theory, first of all, the reactant molecules must form an activated complex or transition complex, which then decomposes to form the products. The transition complex which has been formed, then that transition complex then decomposes to form the activated complex, decomposes to form the product. The reactant molecules having sufficient energy, must collide with each other. First of all, there is a collision between the reactant molecules is takes place. Suppose that A and B are the reactant molecules. They undergo collision, and these reacting molecules then form the activated complex. Suppose that this is the activated complex, AB star, it is the activated complex. Okay, it means that each reaction has an activated complex, and that is also the characteristics of the reaction. In every chemical reaction, according to this concept of the activated complex, the reactant molecules must collide. They are having the sufficient energy and they undergo the collision. And due to the collision between the reactant molecules, they are converted into the activated complex. And later on, this activated complex converted into the product. So this activated complex decomposes into the product. So the activated complex is supposed to have a transient existence only. Means supposed to be, it is the intermediate step of the chemical reaction. This is called as an intermediate step of chemical reaction. So once the activated complex has formed in the reaction, it must be undergo the decomposition and it is converted into the product. So the rate of the reaction is given by the rate of decomposition of the activated complex for the reaction. So in such reactions, the rate of the reaction is given by the rate of decomposition of the activated complex into the product. Now you have see here the example. The two reacting molecules, that is hydrogen molecule and iodine molecules, are going to react. So collision between them takes place and there is a formation of the intermediate complex. So you can see here the hydrogen and iodine, there is a linkage is formed here. Okay, so this is the activated complex and there is a rearrangement of valence bond and energy must be takes place and there is a formation of the activated complex, and once this activated complex is formed, it is converted into the product, that is twice Hi molecules. So this is the reaction where H2 molecule react with I2 molecule and it is converted to the product hydrogen iodide. But in this process, there is a formation of this activated complex. And once this activated complex is formed, then it is decomposes to this product hydrogen iodide. So the rate of the reaction is depends upon the rate of decomposition of this activated complex into this product. Okay. So in the activated complex theory, the energy of activation is defined as the excess energy which the reactant molecules must acquire to form the activated complex. To form the activated complex, some energy is needed. Then and there, the reactant molecules are goes into the activated complex. So the energy of activation is required for the reactant. So what is the energy of activation? The energy of activation is the excess energy which the reactant molecules must acquire to form the activated complex. Okay. So you can see here the graph of potential energy where against the reaction path. So you can see here the reactants hydrogen molecule and I2 molecule. Their energy is less, but if we supply some energy to these reactant molecules, some excess energy to these reactant molecules, then they are converted into the activated complex. Okay, so this much difference, it is the energy of activation. You can see that. Okay. Once the reactant molecules goes into the activated complex, they will be decomposed into the product, that is HI. Okay. So this is the difference between the enthalpy of a product and enthalpy of the reactant. So that is delta H. It is equal to enthalpy of the product P minus enthalpy of the reactant R. Okay. So and energy of activation, this is the excess of energy required to the reactant molecules. Then that reactant molecules will be goes into the this activated complex. Now, by applying the statistical thermodynamics, the Eyring derived an expression for the specific rate of the reaction. So, for such reaction, he derived the expression for specific rate of the reaction, and he obtained the rate constant K. So, the rate constant K for the reaction is given by the equation. So, you can see here the rate constant for the reaction is given by this equation where K it is a rate constant, K it is equal to RT into K star divided by NH. This is equation 1 here, and this equation has given by the Eyring. In this equation where N is the Avogadro's number, H is a Planck's constant, R is a gas constant, T is the temperature, and K star is the equilibrium constant for the equilibrium between the activated complex and the reactant. This K star, it is called as a equilibrium constant because the reactant molecules are goes into the activated complex. So this K star, it is the equilibrium constant for the activated complex. This is the equation given by the Eyring where K is the rate constant. It is related to the equilibrium constant here. Now the relation between, now we are going to simplify the equation here. The relation between standard free energy change and equilibrium constant, it is given by this equation is known to us, delta G, or the similar equation belongs to this is also known to us, that is delta G0, it is equal to minus RT ln K. Okay, this equation is known to us where delta G0 it is the standard free energy change and K is the equilibrium constant. So this is the relation between the standard free energy change and the equilibrium constant. So we can write this equation now, delta G star, it is equal to minus RT ln K star, where K star it is called as a equilibrium constant. Now this relation can also be written as, we can simplify this equation. So we can write here ln K star, it is equal to minus delta G star divided by RT. So therefore, K star it is equal to E raised to minus delta G star upon RT. Okay. So we can write the equation in this way. This is K star it is equal to E raised to minus delta G star upon RT. This is our equation. But in thermodynamics, we know that delta G it is equal to delta H minus T into delta S. The free energy change it is equal to enthalpy change minus T into entropy change. So delta G star we can write here delta S star minus T into delta S star. So we can substitute here delta G star. So this equation 3 can be written as, so we can write the equation 3 in this way. K star it is equal to E raised to, so put here minus delta G star by this equation. So minus sign should be here out of the bracket here. So we can write delta G star, that is delta H star minus T into delta S star. Okay. It is divided by RT. Now we can separate the terms here. So you can see this equation K star it is equal to E raised to delta S star upon R. So this is minus minus plus, T get cancelled here. So it is E raised to delta S star upon R, and it is E raised to minus delta S star upon RT. So we are getting this equation here, where delta S star and delta S star are the standard enthalpy change and standard entropy change. Okay, standard entropy change of the activation. Now substituting the value of the K star. Now we are having the value of the K star here. So this value can be substituted in equation 2. So we are having this equation 2 here. You can see this is the equation 2. So we can substitute the value of the K star in this equation. So let us substitute the value of the K star in this equation. So we can write here, we can substitute this in the equation 1. We can substitute this in the equation 1. So we can write here K equal to RT upon NH. Okay, so K star it is E raised to delta S star upon R into E raised to minus delta S star upon RT. So we substitute here K star in equation 1. So this is now the equation 4 here. Now we can simplify this equation also. So you can see here. So we obtain this equation K equal to RT upon NH E raised to delta S star upon R into E raised to minus delta S star upon RT. Okay. So supposed to be this is our equation 4. Now comparison, the term RT upon NH is constant. Remember this, R is a constant. Suppose temperature is constant here, N is the Avogadro number, H is a Planck's constant. So this term RT upon NH, it is constant here. Okay, and at a definite temperature, and it is independent of the nature of the reactant. Okay, so comparison of this equation 4 with Arrhenius equation, we are having this Arrhenius equation. So we can compare these two equations now. So this is also the rate constant. According to the Arrhenius equation, K is equal to A into E raised to minus E upon RT. Okay, so this is also K equal to RT upon NH E raised to delta S star upon R. So we can compare this equation now. Okay, so you can see here what we get. The new equation we can obtain here. So A, it is a frequency factor. So we can write this is A here, RT upon NH into E raised to delta S star upon R. Supposed to be this is A. Okay, this is A. And E raised to minus E upon RT, that is E raised to minus delta S star upon RT. Okay, so Arrhenius equation can be compared here. Okay, so then we can take logarithm on both sides of the equation 4. So taking logarithm on both sides of the equation 4. So ln k is equal to ln RT upon NH. So this is now delta S upon R. This is now minus delta S star upon RT. So taking logarithm, we are getting this equation. Suppose that this is equation 5. Okay. So in equation 5, we get here the rate constant K. Okay. So this equation 5 is the fundamental equation of the transition state. Fundamental equation of this activated theory. So in transition state theory, the value of A has a different meaning. Okay, so this is about the relation between the rate constant K with entropy change, standard entropy change with the standard enthalpy change. Okay, so this is the equation 5 we are getting here. For a gaseous reaction, it is observed that entropy of activation delta A star is negative. This means that the system becomes more orderly. That is, molecules get properly oriented before going for activated complex. Thus, the theory explain the failure of the collision theory also. Collision theory does not explain this. In collision theory, there is not proper orientation of the molecules. But this theory explains the proper orientation of the molecules because for a gaseous reaction, the entropy of the activation delta S star, it is negative. So this entropy change, it is a negative for the gaseous reaction. Okay. So this is the fundamental equation of the transition state theory. So in this way, we can obtain here the rate constant K, this equation. Let us once again, I would like to repeat this. You can see here concept of activated complex theory. So in this case, when the reactant molecules coming towards to each other to react, there is a formation of this activated complex. Okay. So for this purpose, minimum excess of energy must be supplied to the reactant molecules. That is called as the energy of activation. And if this energy is sufficient, then the reactant molecules goes into the activated complex, and later on that activated complex get decomposes into the product. Okay, so the rate of the reaction is given by the rate of the decomposition of the activated complex. The rate of the reaction, it is given by the rate of the decomposition of this activated complex into the product. So this is the example is taken here, reaction between H2 and I2, where there is a formation of the activated complex. So you can see this is the formation of the activated complex, where this is the product. Molecules are formed here. Now the reaction path can be shown here. You can see the reaction path. Okay, two molecules are undergo collision. If minimum excess of energy is supplied to the reactant molecules, they are goes into the activated state or transition state. Okay, so this difference, it is called as the energy of activation. It means that to goes into the activated complex, some energy is required. So they once they acquire the energy of once they activated, they are converted into the product. So Eyring has given the equation for this. So according to the Eyring, the rate constant K for the reaction, it is given by, so this is the Eyring equation, K equal to RT into K star upon NH. This equation has been given by the Eyring, or this equation it is called also Eyring equation, where K star it is a equilibrium constant, N it is a Avogadro number, H is a Planck constant, and K it is called as a rate constant. Okay. Now we aware that the standard free energy change and equilibrium constants are related by this equation delta G star, it is equal to minus RT ln K star, or delta G0, it is equal to minus RT ln K0. I think this equation is also called as want of reaction isotherm, delta G0 equal to minus RT ln K. Okay. Now we can simplify this equation now. Okay. So by simplifying this equation, we are getting this equation now, equation 4. Okay. And by taking the logarithm on both sides, finally we obtain this equation, that is ln K equal to ln RT upon NH plus delta star upon R minus delta star upon RT. So this is the modified Eyring equation. We have reduced the relationship between the this rate constant K with the entropy change and with the enthalpy change. Okay, so this is about the concept of the activated complex theory. So in the concept of the activated complex theory, there is a formation of the activated complex. There is a formation of the activated complex.